So hello again. Tonight we're going to talk about gravitational wave memory. We've had 3 presentations involving gravity waves so far, and we'll do one more next week that's kind of electromagnetic spectrum, gravity wave spectrum related, associative, and then we'll do other topics. So if you think I'm only ever going to do gravity waves ever again, one more week after this one. So they've known that they've had observational confirmations that gravity waves exist since LIGO did it in 2015. And gravity waves, if people don't remember, that's high gravity waves or ripples in the fabric of space-time. Big Al Einstein predicted them in 1916, but also said we'll probably never be able to observe them because he couldn't fathom the laser interferometry observatories like LIGO and VIRGO and KAGRA. Gravity waves have properties like waveforms do, wavelength and frequency, amplitude and phase. And within the last 2 years, I'd say they realized that there seems to be a gravity wave background, much like there is a microwave background, because they started looking at gravity waves of different wavelengths. And they're all different wavelengths. Some of them get really long, like light year plus wavelengths. Gravity wave background exists. They're not quite sure as to all the possible sources of gravity waves. The easy ones they've already figured out, like stellar remnants and black holes and supermassive black holes and colliding and merging things. But there's some that are unaccountable, and those are the ones that have the very long gravity waves. Whenever they detect a gravity wave, and if you have multiple observatories, you can triangulate kind of where it came from. If there's nothing in the foreground, then they'll just say it came from that galaxy over there, because they have no way to pinpoint exactly where the gravity wave came from. And gravity waves suffer from the same light speed distance travel problem that electromagnetic radiation does. So I was reading watching another Anton Petrov video, and he was talking about the recent conjecture that when the gravity wave rolls over an area, that it might impress a fingerprint onto the area that it rolled through. That means that the fabric of space would have this imprint, planets and moons and dust, and as the gravity waves rolled through, it would leave an imprint. Well, we're used to things imprinting, like waves on a shore leaves ripples on the sand, glaciers moving through carve out rocks and stuff, water and wind carve things as they go through. So given a gravity wave, why wouldn't it leave an imprint? The difficult part is, okay, if you think it's going to leave an imprint, do you have any evidence of the imprint itself? And the only evidence you would have is if it changed something. But given that gravity waves pass through us all the time, and we don't even notice that it happened, let alone have any disastrous effects, how would we detect this imprint? At the moment, there's no technology that can observe these gravity wave fingerprints. They've realized that gravity is the kind of weakest thing, the weakest force. Even though gravity is not really a force, it's a change in fabric of space-time, and we just realize that as if it's a force. But look, you can defeat gravity just by doing that. Very weak force. We also know that gravity waves can exist with extremely long wavelengths to maybe billions of light years, and have extremely low frequencies in the range of pico to attoseconds, low amplitudes like femtovolts, low energies per wave occurrence, which is like 10 to the minus 18 electron volts. Almost nothing. But also, since gravity waves have kind of existed since the dawn of the universe, and they've passed through everything, you would think that collectively they would have left some kind of mark. And that's what they're assuming, is that gravity wave leaves a fingerprint. But if gravity waves have even less of an impact than, let's say, neutrinos at least at low probability cause an excitation of other things, which causes them to produce photons, to produce this blue light called Cherenkov radiation. And so we have observatories that can detect Cherenkov radiation. And when we see it, we go, it must have been a neutrino, but we don't directly detect the neutrino. So as we get to longer wavelengths and weaker energy levels, we don't directly detect anything. We indirectly detect things. And what they're trying to do is detect really long gravity waves by staring at the cosmic microwave background in polarized light. And whenever they see a ripple roll through there, the pixels move around. Must have been a gravity wave, but they don't have any recorded evidence of that yet. But they're working on it. They've got 2 observatories that will be up and running soon. If they find a gravity wave of a very long wavelength, that's not its actual event duration. If that gravity wave was pointed at us and passed through us, even though it may be light years in length, it would ripple through us at the speed of light, and we wouldn't even know that it happened. How do we know that a gravity wave leaves a fingerprint, and what would the fingerprint be? There's different kinds of gravity waves. Along the bottom, you can see the various types of observatories used for detecting the shorter, medium, longer, and very long gravity waves. Each of these observatories can only detect a specific wavelength of gravity wave, and there is no one instrument that can sense all of them. So if the gravity waves are using their energy to impress this fingerprint, that's not very much energy. If it did expend the energy, it would be reducing the energy over time to the point where the gravity wave would diminish. If you don't have very much energy, then you don't leave very much of a wave or a ripple. If you think of ocean or a body of water like a lake, and if you start a ripple, if there's not enough energy in the ripple, then if it encounters like a sandbar or a ridge or something like that, the wave will diminish and not make it further. It'll just wash out. If it's larger, then it can go around things. You've often seen, like, if there's a rock sticking up in a lake and a boat goes by, the wave encompasses the rock and then keeps going beyond the rock. But that's assuming you have a lot of energy. Gravity waves are the weakest thing, then they're not going to have enough energy to expend a lot of it interacting with things or leaving a fingerprint on them. Then again, it's not just things like moons and planets and stars that occupy space and space-time. There's also gas and dust. So if the gravity wave was going through a nebula, even though it didn't hit any stars or planets, the gas and dust should move, should have a fingerprint registered on it, but we're not seeing that at the moment. So here's the standard chart of particles, and this is what stuff is made up of. And there's really only 3 things that a gravity wave could imprint on or change. That's the mass of the particles. But if the mass of the particle changed, it might become a different kind of particle. So we would see transitions. If the charge of a particle changed, we'd have new entries in this table, which we don't. If the spin of the particle changed, that's not really something that happens with particles. They keep the same spin amount, and all they do is they flip, spin up or spin down, spin left or spin right. The only mutable thing would be spin, but we'll cover that in a moment. So how would you imprint the fact that a gravity wave had gone through here? Space-time does not have 3-dimensional coordinates. If the gravity wave goes through and it alters a location in space-time, there's no way for us to find that location again because there's no grid of space-time. There's things in space-time, but space-time itself has no grid. There's no way to say, did space-time get moved, bent, and then stay there? We don't have a way of dealing with that. So just asking. So let's say a gravity wave rolled through and it caused new particles to exist, new photons to come into existence, kind of like neutrinos create Cherenkov radiation. We'd see the additional particles. But if it really caused new particles to exist, given that the gravity waves are everywhere and happening all the time, we should have seen something, but we haven't. There's only one theoretical thing that they identify, and that's something called a pulsar cocoon. This is gravity interacting with the energy emissions of a pulsar, causing the shape of the energy emission to change and make kind of a shell around the jets coming off of the pulsar. They're just guessing that that's why it has that shape. It may just be encountering magnetic fields or changes in density. Have to wait to find out. But I don't think it's going to be new particles coming into existence because of gravity waves, because there's been so many gravity waves. We ought to have an enormous number of particles that are new. If you've ever watched, as the saying goes, flotsam floating on water, and the wave goes through and the float bobs up and down, but doesn't really get displaced much. Same sort of thing in space-time. If a gravity wave came through and it moved something, it moved a particle from one location to another, that means the particle would accelerate. It would have a velocity in a certain direction. It would accelerate, and if nothing stopped it in space, it would continue to accelerate. So stuff would kind of like a stellar quake exists, and it blows material off like a red giant. That material wave goes out from the star. Well, if a gravity wave rolling through an area caused a big displacement of gas or dust, it would continue to make that move. And we're not seeing that. So I don't think it's that gravity waves cause displacement of material, particles, matter. Spin. As I mentioned, one of the things that could be changed with a particle, especially electrons and photons, is their spin. If a fermion were to have its spin changed, its spin value would still stay 1/2. And if a boson had its spin value, flip from up to down or down to up, its spin value would still be a 0 or a 1. So it's not going to change the spin value, it's just going to change the spin direction. But we do that all the time. We use magnetic fields to alter the spin. MRIs, when you go in for an MRI, there's a giant superconducting magnet in the MRI machine. That's that clacking you hear. And what it's doing is it's producing a giant magnetic field that changes the spin from random to in a specific direction for all of the hydrogen in all of the water molecules in your body. And that magnet holds them in place. And when the magnet releases, now all of the hydrogen can now spin back to a random level. And when it goes from fixed to randomly spinning, it spits out a photon, and that photon's at a certain radio wavelength, and that's how the MRI detects things. But if gravity waves did that same sort of thing, it would produce a charge. It would produce a change, and we're not seeing that change. Unlikely that spin's being changed by gravity wave fingerprints. What about energy level? If a gravity wave had to expend energy or create more energy, we would have seen that in observations of other particles that got in the way of the gravity wave rolling through. But the energy level of really long wavelength gravity waves is minute fractions of an electron volt. So I'm not sure they would have the energy to transfer to other things. I don't think it's imprinting it in the energy of particles. So in summary, cosmic gravitational wave background exists, gravity waves exist. We're learning new things about them all the time. We're creating new kinds of instruments that will measure longer and longer gravity waves, but we're not detecting them directly, just indirectly with new and fancy instruments. But there's this conjecture that gravity waves rolling through an area, even though you don't feel them and you see no adverse effects from them, somehow the gravity wave, because of its massive size and collective large energy, it should leave some kind of fingerprint. They have yet to find out even one impression or memory of a gravity wave rolling through an event, likely to be short-lived. If it disturbs a location, things are moving randomly. If it disturbs a spin, they're going to spin randomly back the other direction. If it produces energy, it's going to transition, produce a photon, we'd see the photons in whatever wavelength, whether it's radio or infrared or visible or ultraviolet or X-ray or gamma, we would be able to detect that, and we're not. Who knows if pulsar cocoons are going to be the gravity wave fingerprint? I don't think so. I think it's probably going to be magnetic fields or density of the area around the pulsar jets. But keep looking. That's how science figures these things out. But maybe they'll figure it out soon. But in the meantime, I'm just asking. And links. Okay. Next to the last in the series of gravity wave topics, we'll get over, we're past the hump. We're on the way out.
Very nice.
Comments, questions?
So what significant information would you get from these gravity wave fingerprints or memories?
Well, that's the interesting thing is they say, they're conjecturing that much like anything else that rolls through an area, it kind of leaves a fingerprint. Gravity waves, given how big they are and the fact that they're happening all the time, they should leave some kind of fingerprint. But nobody's willing to stand up and go, I think I've identified what the fingerprint might be, and it's this. We should go looking to create an observatory that would look for those things. It's kind of like Cherenkov radiation. That was something that they paid a lot of attention to as just an interesting side effect of water-cooled nuclear reactors. So if you remember which was it, Dr. No, the James Bond movie, they had the prop water-cooled reactor that they fell into and suffered no harm. And then Dr. No actually disappeared and drowned in it. But it had this glow. Well, that glow was not supposed to be white like white light bulbs. The glow is supposed to be blue because that's the particular wavelength of Cherenkov radiation is towards the blue end of the spectrum. They're actually building arrays of telescopes that only look in that particular wavelength of deep blue light so they can detect cosmic neutrino interactions in the atmosphere. And we've got these, if you remember the neutrino detector in Japan, that there was a recent video about the damage that occurred to it because glass is not durable under the presence of large forces. But that's what they were doing. They were looking for this particularly dim blue light caused by neutrinos interacting with water molecules, with the hydrogen and water molecules on a very random basis. And so what they're trying to do is, if we can conjecture there's a gravity wave fingerprint or memory, then if we can find out what change takes place in what particles, now we can build an indirect detector to see when a gravity wave rolls through instead of this interferometer thing that we have, or using pulsar timing arrays, or just staring at the cosmic microwave background looking for a ripple in the pixels. This would give us yet another kind of instrument for looking at gravity waves, not current gravity waves, but gravity waves that have long ago moved through an area. If you've ever watched Calm Lake, when it starts to rain on it, the first raindrops make waves on the surface of the water. But as you get more and more raindrops, not heavy rain, but just more and more rain, eventually the surface of the water becomes chaotic because every drop wants to make its own ripple, and the ripples can cross over each other and cancel each other out. So the shoreline will see a ripple, but out on the open water, it's just chaos. And if the number of gravity waves that are interacting all the time is actually interacting all the time, and it left any sort of fingerprint, it would be creating a chaos of these fingerprints, and we don't see that. Or maybe it's currently invisible and our instruments just can't see it. Maybe it's another attribute of particles that we just haven't realized yet. But
aside from the fact that, okay, there were gravity waves that passed through here, which I think we can infer because there are currently gravity waves, would it give us any other information like, I don't know, different makeup of stars in the universe, or when they came through, or something that would be of interest other than, okay, there was a gravity wave?
Yeah, the only thing I can think of that would be analogous to it is we go to Antarctica and we drill deep ice cores, and then we come back and we look at the ice cores and we go, look, 200,000 years ago, the atmosphere was like this because things move through. Or we go, there must have been a planetary wide fire of some kind because we find a lot of charcoal at this layer. Or
yeah, exactly. So that's what I'm wondering. What can these gravity waves tell us aside from, well, there was a gravity wave?
Well, if we could find what the fingerprint consisted of, and we could, identify and measure them on a regular basis, we might look at a large open plane of material, like a rocky plateau. And if we could find a way to drill into the rocky plateau and then measured the gravity wave fingerprint in all those coring samples, we might detect when a big gravity wave rolled through 1 million years ago. Or we might detect that, well, we see the gravity wave and it kind of starts on this side and it gets weaker on that side. So the gravity wave must have come from that direction. So that there's all sorts of interesting tidbits that you can indirectly derive once you can identify what the gravity wave fingerprint would be, trying to look at historical science. I still have on the edge of things this, once we can detect a wider variation of gravity waves, we might find that a long time ago, the folks that live way out there gave up on modulating the EM spectrum, gave up on radio for interstellar communication, gave up on lasers for interstellar communication, and started generating gravity waves and modulating them, and they communicating gravity waves. So once we can detect wider ranges of gravity waves, we may find that there's modulation out there that we then have to learn how to decode. And then we have to not only decode the digital signals from it, but the languages. You know, if all of a sudden you invented the FM radio and you started receiving specific channels that were originating from Cuba off of Florida, and you didn't speak Spanish and didn't know what Spanish was, you wouldn't know what you were listening to, but it made noise. So the same sort of thing. Once we have the ability to receive gravity waves of all different kinds, we may detect a pattern in them. If we can see over time the gravity waves that have gone through, we may detect a pattern in them and then decode the pattern and find out, well, kind of the verdict's in that there's something out there that is modulating gravity waves, and nature doesn't do that kind of thing. The people that say, may you live in interesting times. Well, we're living in interesting times and it just keeps getting more interesting and more. So, yeah, I'd like to believe that they're going to find a gravity wave fingerprint. They're going to detect it and then do new and interesting things with it. But it may also just be they're looking for more project money, and this was something somebody hadn't thought up yet. So go to it, guys. Any other comments or thoughts? Otherwise, I'll stop recording. Hearing nothing.